Hello everyone, welcome to this video. In this video, we shall be solving this question which states that if G is a set which consists of all 2 cross 2 matrices, right, where all the entries they are the same, right, and they are taken from the set of real numbers such that they are non-zero numbers, right. This is our set. So here within the set, we need to show that this set is a group under the operation of matrix multiplication, right. This is one thing that we have to tell. Another thing that we have to tell is why each element of G has an inverse even though the matrices have zero determinant. So clearly you can see the determinant of this matrix is 0, but they are saying this matrix possesses an inverse. Why is that so? So let's see the solution for this. First of all, we'll be proving that G together with this matrix multiplication, this forms a group, right. We need to show this thing. So in order to prove that it is a group, we need to prove four properties. One is the closure property. What does this closure property tell you? It tell you that if you take any two elements from the given set, so let's consider. So let us take the element A, capital A, as the first matrix, which is A, and A, and let's take another matrix B as some matrix consisting of the elements B, and B. Now if we apply onto these two elements the operation of matrix multiplication, so that means we are just multiplying these two matrices, correct? So how you might be knowing how to perform matrix multiplication. So it would be AB plus AB, here also it would be AB plus AB, here also AB plus AB, and here also AB plus AB. So once you simplify it, it would become 2AB, 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 and 2AB, right? Now you see, if the element A and the B, if they are real numbers, this would imply 2AB is also a real number. If that is so, then this thing would belongs to your group G. Hence, our closure property is satisfied, correct? So we have our first property there for this set G. Closure property is satisfied. Let's move on to the second property. The second property is that of associative property. For the associative property, matrix multiplication, that is associative in nature, right? As matrix multiplication is associative, right? Therefore, our operation here is also, as matrix multiplication is associative. So we have this associative property with us, correct? Now let's move on to the third property, where we need to check whether the identity of this group exists or not. So let's see the existence of identity. For the existence of identity, we are basically looking for a matrix such that if we take this A from this given group, the given set G, then we are looking for some matrix here, right, such that if we have A here, we would get back again A. So what is this, right? We are looking for this. So you can clearly see, if you take this as some X initially, right, let's take this as X. So if you take the left hand side and multiply it, then what would it be? It would be AX, 2AX, 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 and 2AX. So we are looking for the value of X, right? This is solving simple algebra. So this would reduce to simple equation here. How? Now you can compare the entries, right? Because the left hand side, this is the right hand side. So the left hand side and right hand side, they are equal to each other. Hence, from here, 2AX is equals to A. From here, what is the value of X? It is A divided by 2A, which is 1 by 2. So you have got your identity. Hence, the identity matrix. Now, you might be thinking that the unit matrix in this case is the identity. The identity matrix for G is, what is it? 1 by 2, 1 by 2, 1 by 2, and 1 by 2. Why? Because the value of X turns out to be this, and not the identity matrix this, correct? So you should keep this thing in mind. Hence our third property is also satisfied. For the fourth property, we need to check for the existence of inverses for each of the elements. So basically in this case, if we take some element, this matrix, so we are looking for some member here such that it is now the unit element. What is the unit element? It is 1 by 2, 1 by 2, 1 by 2 and 1 by 2, right? So let's again take this as x, x, x and x. So we need to determine what is this x. So again, let's solve the left hand side. So it would be a multiplied together with x, x, x and x. So once you multiply it, you would again get 2ax, 2ax, 2ax and 2ax, right? Now this thing is equal to what? It is given to be equal to 1 by 2 and 1 by 2, 1 by 2 and 1 by 2, right? Which is your right hand side. So from here on comparing, you would get the value as 2ax is equals to 1 by 2. So what is the value of x from here? It is 1 by 2 and divided by 1 by 2a. So it is what? It is 1 by 4a, or you can write it as 1 by 4a inverse. So the value of x is this. Therefore, the inverse matrix of this matrix A is what? It is 1 by 4 times of A inverse, A inverse, A inverse and A inverse. Now obviously A inverse is a real element. Hence you have got the inverse for each of the element. Thus all the group axioms are satisfied. Hence we say this G together with the operation of matrix multiplication is a group, right? One part of the proof is done. Now for the second next part, we need to explain why each element of G has an inverse even though the matrices have zero determinant. So the answer lies in this fourth part only. Here you clearly saw we have found the inverse of each matrix, whereas where the determinant of each matrix is 0 here. So this is possible within this group. Hence we say it forms a group and it has the inverse for each element even though the matrix the determinant in this case is 0. Hence we have satisfied our property, and this is the result. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.